Welcome to the 37th session of LMS for the program BSc and subject mathematics for 5th semester, and the title of the paper is Numerical Analysis. So the third unit of the numerical analysis is finite difference. In that, today we are going to see in this session the properties of delta and E, forward difference and shift operator E. So before we will go, we will have a recap what we have read in the last session. We understood the relation between forward difference, backward difference and the shift operator. Now at the end of this session, we can able to understand the properties of forward difference and the shift operator. So properties of delta and E, that is forward difference and the shift operator E. So here is the first property. Forward difference of a constant function is 0. If you apply a forward difference to the constant, then its value will be 0. So you can see it here. So proof for that one, let f of x is equals to c. We have taken it where c is a constant. Now I have to apply the forward difference formula for this one. So f of delta of f of x, what does it say? F of x plus h minus f of x, right? So it is nothing but a forward difference. Therefore both the values are constant, so it is 0. Similarly, delta of a of f of x, that is a is a constant, it can be written as a into delta of f of x. That means we cannot apply the delta forward difference to a constant. We are applying here to a function. Forward difference is applied to a functions. So here where a is a constant. Okay. Now delta of a into f of x, where a is a constant, we know that. Anyway, I will think that this whole part I have to change. Wherever x is there, I have to change it to x plus h for forward difference formula. So a as it is, f of x plus h minus f of x. Where x is there, x has been changed by x plus h. Right? So if you see in this, I can take a as a common. A I have taken it as a common. A I have taken it as a common here. Now what is this? This part is nothing but an f of x plus h minus f of x. That is nothing but a forward difference. So I wrote that. So you can see it. I have taken it as a delta into a into f of x, but we have got as a into delta of f of x. It means that we can keep the constant outside and we can apply the forward difference to the functions. Right? Okay. Next. Third one. A shift operator E into a into f of x is equals to a into e into f of x, where a is a constant. That is, constant can be kept outside and a shift operator should be applied to the function only, right? So very simple, it's proof. We have considered that e into f of x, e into a into f of x. So what is the definition for the shift operator? It is nothing but e of f of x is e into f of x is equals to f of x plus h. Right? Wherever x is there, x should be replaced by x plus h only. So a as it is f of x plus h. Now you can see this part only, f of x plus h. It is nothing but an e into f of x. Therefore a into e into f of x. That is, a shift operator is applied to the function, not the constant. Constant should be kept as it is. It is just like a differentiation, we can say. Right? Differentiation is applied to the functions. Right? Now here is a fourth one. If m and n are the two positive integers, then m delta forward difference to the power of m, forward difference to the power of n, that is delta to the power of m, delta to the power of n f of x is equals to delta to the power of m plus n into f of x. We can say the bases are same, we can add the powers like that it is. Okay. So we'll start this now. So I have considered that LHS delta to the power of m into delta to the power of n of f of x, right? So delta, I am writing here delta, this delta to the power of m, we are writing it here. This can be written as delta into delta into delta into delta into delta into, like this. How many times we have to write it? It is nothing but an m times we have to write, right? I wrote it into delta to the power of n of f of x kept as it is into f of x. Okay, this part is kept as it is here, right? Okay, now what I will do it, I will take one delta outside, right? So if you take one delta from here outside, means what happens? One delta is taken off, so it should be m minus 1 times of delta will be left. So I have wrote that here, m minus 1 times of delta times. Okay, so here outside delta means what we can say, already delta to the power of n is there, one more delta we have outside, so it will become delta to the power of n plus 1 times of f of x, right? So now similarly, if you take another one delta here outside, how many will be left out? Before that one there is m minus 1, now that means I am reducing 1 by 1 delta. Okay, now if you take the delta outside, it will become delta to the power of n plus 2 times of f of x, right? So similarly, if you go on like this, only delta will be left, means what we can say, m minus 1 times of delta will be there to the power, I can write it. So delta to the power of n plus 1 into delta to the power of n plus m minus 1 into f of x, right? So if you take this one also here inside, what happens? It will become delta to the power of n plus m into f of x. Hence my proof. That means we can say that deltas are there, we can add their powers when product is there. If a and b are any two, next problem we will go for. If a and b are any two real numbers and f of x and g of x are any two functions, then I have to show that delta times of a into f of x plus b into g of x. This can be written as this can be written as a into delta of f of x plus b into delta of g of x, right? That one we have to write it here. That means this delta can be applied to the first function f of x, and again it should be applied to the delta of g of x. Again, once again we can apply it, right? So like this. Now we will have a proof here. Now I have considered this LHS, delta times of a of f of x plus b of g of x is equals to, what we can say, what is this? This is a function, I can say, with constants are there, let it be. So for I have to apply for this part the forward difference. What does it says? Forward difference says that where f of x is there, delta of f of x can be written as f of x plus h minus f of x. That formula I am applying it. Okay, now you can see it here. A into f of x plus h minus a into f of x, right? This is first. For this one I have applied it. Plus is there, plus b into g of x plus h minus b into g of x. Forward difference I have applied, just simple. Okay, now what I will do, I will take off the a here common. If you take outside a, what will be left out? F of x plus h minus f of x plus b times of f of x plus h minus g of x. So what happens here? Now you can see it here. What does it indicates here? F of x plus h minus f of x. It is nothing but a delta of f of x. Right? Similarly, you can see it here. G of x plus h minus g of x. It is delta of g of x. So a is multiple, here b is multiple. We can see we have got our result, right? That means delta can be applied to the function by keeping the constant aside. Okay, right. Now next one. So if A and B are the constant and f of x and g of x are any two functions, then if there is a product of function and we will apply delta, then it can be written as f of x plus h into delta of g of x plus g of x into delta of f of x, right? So we will start. We have taken the LHS here. So I will apply the first forward difference, f of x plus h into g of x plus h minus f of x into g of x. That means I am considering this as a one function. Now I applied it. Okay. Now what I will do, I will add and subtract this f of x plus h into g of x in here in the RHS part. Okay. Now you can see it, this part, f of x plus h into g of x plus h, I have kept it here as it is, right? Now I am subtracting this part. I am introducing with subtraction f of x plus h into d of x. I have subtracted this and now I am adding here f of x plus h into g of x. And you can see this function has been kept here as it is. That is minus of f of x into g of x. Okay. Now I will take some terms common here. I will make the bunch here like this. This is my first bunch. This is my second bunch. Okay. So what I will do in the first bunch, in the first these terms, I will take f of x as a common in this part. In this part I will take common as a f of x plus h. Now you can see it here. F of x plus h, I have taken it as a common. So what will be left out? G of x plus h and g of x. Right? Similarly, in the second part, this part, I will take common as a, what is it? G of x. This one I will take it as a common. Here it is. Okay. So what will be the left out? F of x plus h minus f of x. You can see it. Right? Now, so what does this indicate? First term, this part, what does this indicates? This part, if you see this part, it is nothing but an forward difference, that is delta of delta definition, delta of some function, that is delta of g of x. I have to keep this term as it is, f of x plus h, right? So now what I will do, this term f of x plus h I will kept as it is. This is looking just like a forward difference, so delta of f of x, g of x. So plus g of x I have kept as it is. This is again a forward difference formula, f of x plus h minus f, so delta of f of x, right? Now this is my proof, I can say. Now next problem will go for, so if f of x and g of x are any two functions, then I have to show, if you divide the two functions and then you will apply the delta, forward difference delta, then its solution will be like this. Okay. Now we will see this proof. Let us consider LHS, delta of f of x divided by g of x. Now I will think that this is function. Now apply forward difference formula for this part. So this, what does it says? Where x is there, x should be replaced by x plus h minus f of x. But you can see it here. We have wrote that formula. Now I will take LCM here. This part I have taken the LCM. So it will get cancelled. G of x is multiplied with this and g of x plus h is multiplied with this, with f of x is there. Now I will add and subtract g of x and f of x in the numerator. Right? Here in the numerator of RHS, I will multiply with the function f of x and g of x, and I will add this in the numerator and subtract this in the numerator. Now you can see it, this function has been kept as it is, right? So here I will introduce g of x into f of x. I have subtracted it here below. So similarly I have added that below. Now this function I have kept as it is, divided by denominator has been kept as it is. Okay. Now in this term I will take common. In this term I will take common. and in this term I can take common, right? So here I can take common as a g of x, right? Here I can take common as a f of x. I will see that. So I have taken here in the numerator, you can see it here. Here g of x I have taken common, f of x plus x minus f of x plus h minus f of x will be left. Here f of x I will take in common, so g of x minus g of x plus h is left out. Okay. Now this look like a forward difference formula, right? So now what we can say? This is nothing but our required solution, right? So here still there is one step is missing. I can say here it should be I have to take with minus f of x as a common, right? So I will write that. So little bit there will be a change in formula. So this should be with minus sign. This is with minus sign it will be, right? So what we have to take in this? I have to take minus f of x. So these terms will changes. That is f of g of x plus h minus g of x will be there. Simplification. So I will get my result. Fine. So I will check before. Right. It should be with minus sign. You can see it here. It is minus sign is there. Right. So to make it minus, I will take here minus as a common. So what happens? These terms will shuffle. So g of x plus h minus g of x we will get it. So it is nothing but a delta of g of x. This is delta of f of x. So my final answer is this one. Hence my proof. Right. So some of the books for reference. These are the books for references. So thank you friends.